Okay, so much of this presentation is based on a paper that's coming out in print in Icarus next month. And I'm going to start with a little bit of background for those that are not Jupiter cloud experts, and then talk some about two current problems in Jupiter's atmosphere, the ammonia gas problem and the probe cloud problem, which is kind of a new thing to look at. And as far as solutions to these problems, it's mostly speculation at this point. So Jupiter's atmosphere is mainly hydrogen and helium with trace amounts of volatile gases that form clouds. These are water, ammonia, and hydrogen sulfide. And it doesn't get cold enough in Jupiter's atmosphere for H2S to directly condense, so it combines somehow with ammonia to form something and condense in the atmosphere. The Galileo probe actually measured these clouds, but the probe descended into a 5-micron hotspot, which is a region with anomalous meteorology. In thermal infrared images, these areas look really bright because there's less clouds there to suppress thermal radiation from deeper in the atmosphere. This is what the 5-micron hotspots look like in visible light. They're darker than their surroundings because there's less cloud material there to scatter sunlight back. Jim Friedson put this plot together showing our understanding of these hotspots as equatorially trapped waves, and parcels in the atmosphere will bob up and down as these waves propagate through the atmosphere. So in these 5-micron bright regions, you have parcels that are advecting downwards, bringing dry, cold-trapped air from the top of the atmosphere downwards. So now we're ready to look at this ammonia gas problem, which has been around for a while. Global microwave data show that the ammonia abundance in the atmosphere decreases with height, and it decreases in this region of 2 to 6 bars, which is much deeper than where the ammonia cloud forms. And the ammonia cloud is the main chemical sink for ammonia, so it's a little bit of a mystery exactly what's going on here. One possibility is dynamics, another is chemistry and microphysics, which we're talking about today. The Galileo probe actually measured cloud densities using the nephelometer, which is shown partially deployed here before the probe went to Jupiter. And this plot shows some of the data of this 1.2 bar cloud, which is the one that's a little problematic to explain. So it's only a problem when you start to apply a model to the observations of the cloud densities there at 1.2 bars. And this plot from our Fresh Clouds paper shows cloud density rate as a function of altitude, and I have the temperature scale and the pressure scale here. So a little bit about cloud density rate. It's in grams per centimeter cubed per centimeter, and this basically tells you the efficiency of cloud generation based on a little updraft at any particular level. So near where the water cloud base is formed, you have a high cloud density rate, meaning you can very efficiently form clouds there by an updraft mechanism. But around 1.2 bars, you have sort of a dead zone here where none of these constituents efficiently condense. So even if you have an updraft here, you'll very inefficiently form clouds. So this model has been validated by comparison with terrestrial observations of clouds. And when we apply it to the probe site, we can see this problem again. So here on the y-axis, I'm plotting cloud column density observed. These 3 colored boxes show 3 cloud layers measured by the nephelometer. And for 2 of the cloud layers, the ammonia and the water cloud, you can now use this model, which gives this diagonal line, to relate a given cloud density to a required updraft length scale. So an updraft length scale times the cloud density rate or efficiency that I just plotted before gives you the cloud density. So for these observed cloud densities in the ammonia and water cloud regions, you get updraft length scales of 10 to 100, 10 centimeters to 10 meters. And those updraft length scales are comparable to very thin terrestrial cirrus case. So that kind of makes sense for a 5-micron hotspot where you expect large-scale downwelling. So you don't expect a really strong updraft in these regions. A weak updraft is consistent with turbulence within this large-scale downwelling. But for the 1.2 bar cloud, because of the low efficiency, this diagonal line is shifted way to the right here. And to get that cloud density, you need a very strong, very large updraft length scale or a strong updraft. And that's not really consistent with what we expect for hotspot dynamics. So again, here's this dead zone at 1.2 bars where the observed cloud was. And so one possible way to explain this is that maybe there's a new cloud chemistry here, a new cloud that has higher volatility, so it doesn't condense until colder temperatures compared to what we think we know right now for NH4SH. So if this new cloud were discovered, perhaps by much needed laboratory experiments of the ammonia H2S system, then you'd have a new cloud forming efficiency at this level, and you would be able to explain the observed density in terms of a weaker updraft that's consistent with what we know about hotspot dynamics. In terms of the ammonia gas problem, we can look at another process, which is ammonia uptake on heterogeneous cloud particles. So two forms of this would be surface adsorption, where you have ammonia sticking to the surface of other cloud materials like water and H4SH, or bulk diffusion, where you have ammonia actually diffusing into the ice and perhaps forming new compounds like hydrates. So we actually studied this process in the lab at SRI International using a Knudsen cell setup. And with water, ice as a substrate, we studied the adsorption of ammonia gas to that ice, and the adsorption is very rapid and efficient. So we measured the uptake coefficient and found that even at longer times, though, there was still a low level of uptake, which is consistent with ammonia actually diffusing into the ice bulk and releasing more surface sites for continued adsorption. So, but is this effect strong enough to explain the observed microwave observed depletion of ammonia in Jupiter's atmosphere? Well, this plot kind of assesses that possibility. In the x-axis, you have the updraft length scale. So going towards the right, you have very large updraft length scales, meaning very vigorous convection, strong updrafts. And in this case, you have enough surface enough surface on the cloud particles to adsorb more ammonia. So you would require less surface adsorption in terms of molecules per centimeter squared to explain the microwave depletion, which is indicated by this diagonal line. But still, even for very large updrafts here on the right of this plot, the required amount of surface absorption is much higher than than this published estimate of the saturation. So once the surface of these cloud particles gets saturated by ammonia, you can't absorb enough anymore to explain the microwave observations. But bulk diffusion is perhaps a more likely process. So here, the microwave, the amount of ammonia incorporated into the cloud particles in order to match this microwave depletion is in line with the composition of ammonia hydrates for updrafts that are somewhat reasonable. They're stronger than what we see in fluffy terrestrial cumulus, but probably less than we would find in a number of very strong Jupiter superstorms. So it's possible, perhaps, to sequester enough ammonia by having it diffuse into the bulk of other cloud ice particles. So this is all based on, the cloud problem is all based on the Galileo probe observation of a cloud at 1.2 bars, but there are other observations of clouds at 1 bar. This retrieval based on Cassini-Sears thermal infrared spectra of Jupiter by Kachamachiva shows a cloud level at 1 bar, which is in that dead zone in terms of the cloud forming efficiency. So it's possible that there's this observation is also confirming that we need to revise our cloud chemistry. Another study here by Sromovsky and Fry in 2002 compared prior models here on the left of the plot, which all sort of showed a dead zone near 1 bar, consistent with, and that's just based on the equilibrium plots that I had showed before. So the prior cloud models had sort of assumed that the clouds are going to form where the equilibrium model says they should. But Swarmovsky and Fry used a cloud near 1.2 bar and were able to duplicate a lot of, use the cloud there in their models and were able to duplicate a lot of observations in the optical range for HST. So in conclusion, we're using a new fresh clouds model, which is sort of an update to the Wyden, Schilling, and Lewis model. And it's validated by terrestrial observations. And when we apply this to Galileo probe data, we produce a probe cloud problem that we see cloud density at a region where it's not likely that clouds can easily form. So we're looking at potential solutions here that perhaps there's a different cloud chemistry, something else is forming. This was actually suggested in the literature by scientists in Kazakhstan, but it's very difficult to find their papers. So it's possible that there's, instead of ammonium hydrosulfide, you have ammonium sulfide, which is NH4(2)S. So a different composition would sequester more ammonia compared to the NH4SH and possibly condense at a different location. And then another possibility for explaining the ammonia gas problem is that you have significant uptake of ammonia onto heterogeneous cloud particles. And today, December 19th, is my birthday, so only easy questions, please.
So we have time about 2 or 3 questions.
Yes.
Where is the microphone?
Hello, wonderful talk. How do you prove which solution is right?
Well, we need more lab data on the ammonia H2S system. That's one thing. We need more lab data on this uptake into heterogeneous ice particles, figure out what forms there. And we need more models of dynamics to see the relative importance of dynamics in chemistry in explaining these problems. So much more further research. And perhaps observations with the TMT.
Hi, Mike. Nice work. So I'm wondering, is there any latitude dependence on this potential cloud? For example, is there any difference between zones and belts?
Are you talking in terms of observations,
yes.
Radio transfer?
Yes.
Yes, there are a lot of, there are differences, both in the clouds and the ammonia gas. So the microwave observations, when they're resolved, you can see differences in the amount of gas there. We're also looking at spectroscopy of Jupiter in the infrared and seeing how ammonia varies with space there. So yeah, so that definitely does support the influence of dynamics. But there are some dynamical studies that show how convection can deplete ammonia below the ammonia cloud deck, but it's not a magnitude high enough to explain the observation. So it's probably a combination of both.
Okay, thank you.
Mm-hmm.
Okay, one more.
Happy birthday, Mike.
Thank you.
So how does horizontal advection come into play? Because most of the air mass motion is in the horizontal velocity, not in the vertical, right? Atmosphere is, for the most part, aesthetically stable. So how does horizontal advection come in? Like materials come in from the side instead of vertical?
In general in the atmosphere or in 5-micron hotspots?
Even in the 5-micron hotspots, so there's vertical motion, but it's not really convection, like moist convection, right? It's horizontal, like, well, vertical motion is coming in from the wave blowing through the structure. So in that, of course, if vapor comes in, as long as it's not condensing, vapor is still going to be there. But I just wondered if you have thought about how horizontal motion comes in.
Yeah, I mean, I guess you have to look at the magnitude of the motion. So the horizontal velocities are can be 100 meters of 100 meters per second or so. Vertical velocities are probably much slower, on the order of meters per second if it's vigorous convection. So the magnitude is different, and then observationally, if you want to trace horizontal motions, you would look at imaging and watch clouds move. But if you want to trace vertical motions, this is a good way because the temperature changes a lot with height, so you can have condensation and removal of vapor that way. Horizontally, the temperature doesn't change that much, just a few degrees at a given pressure level.
Thanks.
Mm-hmm.
Thank you.